Hi, my name is Burak Bartan. I'll be presenting our work on distributed sketching methods for privacy-preserving regression. This is joint work with my advisor, Professor Mert Bilancı. In this work, we consider the well-known least squares problem of minimizing the squared L2 norm of a times x minus b, and the closed form solution to this problem is given in equation 2. We are interested in the setting where the data matrix A is too large that it doesn't fit in the memory of a single node. And to set up the notation, A is the n by d data matrix with more rows than columns, and B is the output vector. The term sketching refers to multiplying the data matrix and the output vector by the sketching matrix S, which leads to the problem in equation 3. The sketching matrix S is a random matrix that is m by n dimensional, where we call m the sketch size. And when the sketch size is much smaller than n, the number of rows of A, the sketch problem could be solved much faster than the original problem. Solving the sketched problem provides us with an approximate solution to the original large-scale problem. This image here is for visualizing what sketching does. It reduces the dimension of the problem from n to m. There are many possible random sketching matrices in the sketching literature, such as Gaussian, where each entry of the matrix S is sampled from the IID normal distribution, or uniform sampling, which randomly selects m out of n rows. In this work, we consider a centralized distributed model with a single master node and Q worker nodes. We use the serverless computing framework for the experiments. A little background on serverless computing. It is a cloud service that provides access to a high number of compute functions relatively inexpensively without requiring server management. And it shows promise for large-scale computation tasks that can be run in parallel. Now we present the algorithm. This algorithm brings sketching and distributed computation together via averaging. Instead of a single sketching matrix S, here we have Q sketching matrices, S1 through SQ, one for every worker node. In the algorithm, each worker node solves their sketched problem and outputs the approximate solution x hat sub k and sends it to the master node. The master node collects the outputs of all the worker nodes and averages them to obtain the averaged solution x bar. If some of the worker nodes fail or take too long to finish computing, the master node is still able to produce a solution by averaging only the available outputs. And before we give the main result, let us define the cost function as f of x, which is equal to the least squares objective, square norm of a times x minus b. And note that x star is the optimal solution and x bar is the average solution, namely the output of the algorithm from the previous slide. Theorem 1 characterizes the expected difference between the cost of the average solution and the optimal value. And Theorem 1 states that for Gaussian sketches, the error scales with 1 over q, where q is the number of workers. And very importantly, for Gaussian sketches, the averaged solution is unbiased, unlike other sketches. And you can find more about the unbiasedness of Gaussian sketches and the bias bounds for other sketches such as uniform sampling in the full paper. For Gaussian sketches, note that only the master node has access to the data, and the worker nodes only have access to the sketched data S times A and S times B. In a setting where the worker nodes are not trusted, the distributed sketching algorithm preserves differential privacy under some conditions. This figure shows the approximation error against time for the distributed sketching algorithm for a large-scale least squares problem with a data matrix of 20 million rows and 2,000 columns. This experiment was done in AWS Lambda, which is AWS's serverless computing service. We see in this figure that as time progresses, more and more workers return their outputs and their average gets closer to the optimal solution. In summary, in this work, we investigate distributed sketching from the perspectives of cost approximation, runtime, and privacy preservation. And you can find out more about this work and its extension to regularized problems in these papers. Thank you.